Welcome to the supplementary video for our paper, SplatFusion, Training Free 3D Scene Completion from Sparse Views, using Temporal Diffusion Priors and Gaussian Splatting. We'll start with a quick method overview. Let's begin with the motivation behind our work. Reconstructing 3D scenes from just a few unposed views, especially in extremely sparse or wide baseline settings, is a highly ill-posed problem. The main challenges include incomplete geometry, occlusions, and ghosting artifacts caused by naive interpolation. Our goal is to overcome these issues using a training-free pipeline that reconstructs complete, perceptually realistic scenes from only 2 or 3 input images. This is achieved through temporal diffusion priors, which guide the hallucination and refinement of missing regions. Our pipeline begins with a set of sparse, unposed input images, typically just 2 or 3 wide baseline views of the scene. These serve as our only input for the 3D reconstruction task. We first estimate camera poses using dust, 3R, which provide 3D point clouds and camera poses even under severe input sparsity. This forms the initial geometric scaffold for the scene. Using the recovered geometry and poses, we initialize a coarse 3D scene via Gaussian Splatting. This generates an initial 3DGS model and produces renderings from multiple camera viewpoints. However, these renderings often suffer from noise, missing regions, and temporal inconsistency due to the sparsity of inputs. To refine this output, we introduce a pre-trained video diffusion model, guided by our novel module called Scene Consistent Temporal Guidance. SCTG injects both spatial and occlusion-aware guidance into the diffusion process. This encourages the model to fill missing content while preserving geometric consistency across time. The diffusion model encodes the noisy initial frames, refines them frame by frame, and decodes temporally coherent, visually plausible novel views. Finally, the refined outputs are reprojected and fused back into the 3DGS pipeline using back projection and model update, ensuring that improvements at the image level also benefit the underlying 3D representation. The end result is a set of perceptually complete, structurally faithful, and temporally consistent renderings, even under extreme view sparsity. A core contribution of our method is the Scene Consistent Temporal Guidance module, which improves the diffusion process by enforcing structural and temporal consistency during generation. At each denoising time step t, the diffusion model holds a noisy, latent representation xt. To guide its refinement, we render a corresponding reference frame rt from the optimized Gaussian scene. This frame acts as a structural anchor for that time step. We then compare the perceptual features of xt and rt using a spatial consistency loss, computed in feature space using a pre-trained backbone. This loss encourages the output to follow the scene layout encoded in the 3DGS geometry. To handle occlusions and visibility uncertainty, we also apply an occlusion-aware loss, which uses a visibility mask MT derived from the Gaussian rendering. This loss enforces alignment only in valid, visible regions and avoids penalizing hallucinations in missing or ambiguous areas. By injecting this gradient into the denoising loop, we bias the generative model towards structurally valid, occlusion-aware, and temporally aligned outputs, while preserving the diffusion model's natural generative capabilities. We now present qualitative results across a variety of challenging scenes using extremely sparse input views. Our approach refines the initial results, filling in missing geometry and recovering structure in both occluded and unobserved regions. In addition to visual results, we also perform quantitative evaluations across several benchmarks using standard perceptual metrics like PSNR, SSIM, and LPIPS, as well as VLM-based scores that better capture human-perceived realism. Our method consistently achieves the best performance across all perceptual metrics, with particularly strong improvements in LPIPS and structure-aware VLM scores, reflecting better texture detail, and overall visual quality. Thank you for watching this supplementary video. We hope it gave you a clear understanding of our method and its benefits for scene completion under extreme sparsity. For more details, please refer to the full paper.